Ever wondered, what is the strategy behind merge and quick sort? Imagine you need to sort a shuffled deck of 52 cards. You could compare each card to every other card, swap them one by one until everything's in order. That's the brute force approach. And it works. But here's the problem. The number of comparisons explodes. For 52 cards, you're looking at over 2,500 comparisons. Now scale that up. Sorting 1 million numbers the same way? You'd need roughly 1 trillion comparisons. On a typical computer, that could take 3 hours. But there's a faster way, a radically faster way, and it's called divide and conquer. Instead of tackling the entire problem at once, you split it in half. Then split those halves, and keep splitting until the pieces are so small they're trivial to solve. This process of breaking down a large problem into smaller, manageable sub-problems is the essence of the divide phase. Then you smartly merge them back together. This conquer phase involves combining the sorted smaller pieces into larger, sorted ones. This strategy doesn't just shave off a few seconds. It turns hours into seconds. This approach is the core idea behind merge sort and quick sort, two of the most important algorithms in computer science. This visual comparison demonstrates why breaking problems down is exponentially more efficient. The brute force approach, with its order n squared complexity, quickly becomes unmanageable as the number of elements increases. In contrast, the divide and conquer strategy, with order n log n complexity, scales far more effectively, making it a powerful tool for solving large-scale problems. Here we see the complete divide and conquer process in action. First, the divide phase recursively breaks the problem down, splitting the data until each piece is trivial, like a single card. Then, the conquer phase efficiently merges these sorted pieces back together, level by level, until the entire dataset is sorted. This structured approach is what gives us the impressive order n log n efficiency. The efficiency of divide and conquer algorithms like merge sort can be formally described by this recurrence relation. T of n equals 2 times T of n divided by 2 plus order n. Here, T of n represents the time to solve a problem of size n. The 2 times T of n divided by 2 term means we solve 2 sub-problems, each half the original size. And the plus order n term accounts for the work done in merging those sub-problem results. Applying the master theorem to this recurrence relation shows that the overall time complexity is order n log n. This mathematical proof confirms the algorithm's efficiency. Now that we understand the power of divide and conquer, let's look at 2 prominent algorithms that use this strategy: merge sort and quick sort. Both aim for optimal sorting efficiency, but they achieve it through slightly different mechanisms, leading to distinct trade-offs. Understanding these differences will help you decide which algorithm to use when it matters most for your specific application. So how does divide and conquer actually work? Let's walk through it with our deck of cards. The strategy has 3 steps: divide, conquer, and combine. First, you split the deck in half. Then you recursively split each half until you're left with individual cards. And a single card is already sorted, so that's your base case. This phase confirms that once elements are isolated, they are inherently sorted. No further processing is needed at this level, as the smallest units are our starting point for combining. Now comes the clever part. You merge the sorted pieces back together. Take 2 sorted piles, compare the front cards, and always pick the smaller one. Here, we compare the first elements of each pile. The smaller element, in this case 3, is chosen and moved to our new combined output. The process repeats. We compare 5 and 7, select 5, and add it to our growing sorted list. Notice how the pointers always move forward, indicating a single pass. Since both piles are already sorted, you never need to backtrack. You just keep picking the smaller front card until both piles are empty. This is merge sort. The key insight is that merging two sorted halves takes linear time. Just one pass through all the elements. And because you split the deck log base 2 of n times, the total work is n times log base 2 of n. That's why merge sort guarantees big O of n log base 2 of n performance, no matter what the input looks like. To quantify this, we see that for 52 cards, with approximately 6 levels of splitting, the total comparisons are 312. This is a significant improvement over brute force methods like bubble sort, which would require over 2,704 comparisons for the same task. It's predictable, reliable, and the foundation of many real-world systems. Let's see it in action. Merge sort guarantees O of n log n. But it has a cost: memory. Every time you merge, you need extra space to hold the result. Specifically, ON additional memory. That's fine for small datasets, but for massive ones, it adds up. This visualization shows the explicit memory being used to store the merged output. Enter quicksort. Instead of always splitting in half, quicksort picks a pivot, one element from the deck, and partitions everything else into two groups. Elements smaller than the pivot go left, elements larger go right. Then it recursively sorts each partition. The genius here is that quicksort can partition in place, meaning it sorts without needing extra memory. This makes it faster in practice because it avoids the overhead of copying data, a common cost in other sorting algorithms. But there's a catch. If you pick a bad pivot, say always the smallest or largest element, the partitions become unbalanced. Instead of splitting in half, you end up with one huge partition and one tiny one. The tree degenerates into a chain and the algorithm slows down to O(n squared, just like brute force. This shows why the choice of pivot is critical. This illustrates the worst-case scenario where quicksort's performance degrades significantly due to poor pivot choices. To avoid this, pivot selection matters. Randomizing the pivot or using the median of 3 strategy helps keep the tree balanced. This ensures O of n log n on average, or even guaranteed in the case of median of 3 with some overhead. So here's the trade-off summarized. Merge sort guarantees O of n log n time complexity, but uses more memory with O of n extra space. Quicksort is faster in practice and uses less memory, typically O log n stack space, but can degrade to O of n squared with bad pivots. The choice between merge sort and quicksort depends entirely on your specific constraints and priorities. Divide and conquer isn't just an academic exercise, it's the backbone of systems you use every day. When a database sorts 10 million records for a search query, it's using merge sort or quicksort under the hood. When Git merges code from multiple developers, it's applying divide and conquer. Merge algorithms to reconcile changes efficiently. When a machine learning model splits data to find the best decision boundary, it's using the same recursive partitioning logic as quicksort. And when you run a program on a multi-core processor, the operating system can distribute divide and conquer tasks across cores in parallel because each partition is independent. The strategy scales. It parallelizes. It's provably optimal for comparison-based sorting. That pattern applies far beyond sorting to parsing, searching, optimization, and more. But here's the deeper lesson. Divide and conquer is a mental model. It teaches you to break hard problems into smaller, solvable pieces, then intelligently recombine the results. Mastering this concept doesn't just make you better at algorithms. It makes you better at thinking. And that's the real power of divide and conquer.